Hey everyone, this is Intro to Chemistry from start to finish in under 6 minutes. So if you ever feel like you're stuck somewhere or need somewhere to be, then just pause the video and then find a good place and then look at the slide and keep going. Alright, so the first one is significant figures, and this is the number associated with the accuracy of the value, and this is using the Pacific Atlantic rule where if it's present, you count from the left, if it's absent, you count from the right. And there's some examples here. 0.57 has 2 because you start from the left, count from non-zero, and 5001 because you start from the right from the first non-zero. Scientific notation, as you can see, is very useful for very big and small numbers. So for significant figure rules, addition, subtraction, least number of decimal places, and multiplication, division, least number of significant figures. As you can see, in our example, we have the least decimal place is 0.5, which is 1.1, and for our multiplication division, it is 0.57, which is the least one, which is why it's 0.40. Alright, so for the error calculations, 0.64 minus 0.43 equals to 0.21 is the error that we're calculating, and error is basically how accurate or inaccurate your information is, and percent error is basically just the error but in a percent. So you use the absolute value 0.21, as you can see here, divide that by 0.43 equals to 49%. Now for measurement and density, some terms are that density is how packed the object or substance is, mass is the amount of matter which the object contains, and volume is how much space the object takes up. And the formula is D equals to M over V, where mass and V is volume and D is density. Now moving on to some things you need to keep in mind is that include all known digits plus one final digit when you're measuring on a ruler or a certain graduate cylinder or anything like that. For example, instead of saying like just 2, you'd say 2.3 because you're adding an extra estimated digit. Now measure from the bottom of the meniscus when looking at the graduate cylinder. In other words, measure from the tangent of the curve at the bottom when looking at a meniscus. Now, precision and accuracy. Precision is how close together a series of measurements are to each other, and accuracy is how close a measurement is to the accepted value. For example, the left one is not accurate nor precise because they're far apart. Precise but not accurate because the estimated are close together but not accurate. Precise and accurate is at the bullseye with all three. Now, going on to the first experiment, iron, we have the mass to be 81.22 grams and a graduated cylinder, and then basically subtracting that, we get 10.3 milliliters as our volume because you subtract from the basic from the one with the lot. Now this is the calculations for all of them. As you can see, the density we get to 7.89 grams per milliliter, and the percent error is 49%. As you keep on going, you'd see all the values. Now going into the experiment 2, we have a Lego head. I know it's weird. So we got our mass to be 0.55 grams, and then our volume to be 0.48 milliliters. And this is done using just putting it into the water and then measuring again, as you would usually do. And these are the calculations, which is we get the density to be 1.1 grams per milliliter, and the percent error to be 2.8%. Now, the third experiment, gold, we have our weight to be 1,000.3 grams and our volume to be 51 milliliters. This one is a 1,000 milliliter graduated cylinder, while the previous one was 100, and the one before that was 10 milliliters. And then you just kind of measure it by subtracting it, and then we get 51 milliliters. These are the calculations with the density being about 21 grams per milliliter, and the percent error being 10%. Now, going on to kinetic molecular theory and gases. A gas is a phase of atoms where atoms of a substance are in motion to fill a container. Basically, particles are pointing in random directions. They don't really interact with each other. And factors and variables. Pressure is how particles hit surfaces. Temperature is the amount of heat in the system. Volume is how big they are. And moles are the number of particles. And basically, these all have different types of definitions. As you can see in the sub-bullet points. Just pause the video if you ever need to look at it. Now, the relationship between them, pressure and volume, are inversely proportional. As pressure increases, the volume decreases. Temperature and pressure are directly related. As temperature increases, speed increases and collisions increase. And volume and temperature are directly proportional. As volume increases, the temperature increases, and vice versa. Kinetic energy is mostly related to the speed of the molecules and the heat transfer of the temperature. Now, looking at our scenario, a tennis ball of fixed volume is kept left on a tennis court overnight. The next day is incredibly hot. How does the behavior of gas particles change? So in this one, we have the volume, which doesn't change as stated in the question over here, and the number of particles is no change because it's a sealed container, meaning no particles ever go away and none ever come back in. So the speed and collisions are the only ones that can change because the temp increases from night to day, and collisions increase because as the speed increases from what I said before, the collisions also increase. As you can see from these diagrams over here, we have from before when it's cold, basically if there's an O, we have an O, and if there's one quote around them, it means that it is the slowest versus something which is like 3, which is faster. So you just add more to make it more faster. Now going on to carbon and climate, spatial scale is the extent of an area at which the process or phenomenon occurs, and temporal scale is the duration of the time length a thing or process. Now looking at this graph, we have a large temporal scale, amount of carbon dioxide emissions over time, which is as seen over here from the y-axis. 1950 is the highest historical carbon dioxide, as you can see from here in this graph over here. This is from nasa.gov, so it is something that is reliable, and a steady increase until full spike in the last 1,000 years. As you can see, it's a steady increase and then just a big spike up. Now going on to graph 2, there's a shorter temporal scale, amount of carbon dioxide emissions over time, as same thing as last one, as we are just comparing these two. And this is from EPA.gov, which is something that is a reliable source. And things have only gotten worse. As you can see, it's just a steady increase all the way through. Now going on to which one is better? Which one do you think would prove the other person that climate change is in fact real? Well, in fact, the left one is better because of the higher temporal scale, which shows more results. It fully encompasses why the problem, as shown by the unimaginable spike at the end towards the x-axis as it reaches to modern time. It basically shows the other person that's denying it like, whoa, this is actually a big problem. And the person would believe it if it is higher, rather than a steady increase, even though they think that, oh, we could just fix it very quickly if it's only that kind of a steady increase. Now, the effect it has on humans is that from the geosphere to the atmosphere, we humans are burning fossil fuels in the geosphere, which goes into the factories, and then it makes carbon in the atmosphere, which is harder for us to breathe. And another thing is that the biosphere goes to the geosphere and atmosphere. And how does it affect that? Well, we cut down trees, basically deforestation in the biosphere, and that is basically bad ecosystems and ruins the habitats in the geosphere. It also makes less oxygen in the atmosphere. If there's less, it means it's harder for us to breathe, and there's more carbon from what I said here from burning of fossil fuels. And these are some sources and tools that I have used. Basically, this is how I found the measurements of a lot of the items and the accepted values. Image of the graduated cylinders and all of the images that are shown here. There's some more over there. And last but not least, the picture of the gold rock and the 2 graphs. All right, thank you.